So hello, how's everybody doing?
Good, how are you?
Pretty good.
Great, me too.
Thanks.
Welcome to the last week of classes. We made it. It's been a long semester, but we're finally here. So I need to start with some basic logistic stuff, although we've been over all this before. CAP is up now, due Thursday evening, as usual. Exam 4 is Friday. Anytime, I'll post it. I'll post it soon. Well, it will be available starting at 8 a.m. on Friday, and you can take it, I don't know, sometime Friday evening. I'll probably shut it off. But that'll be, the specific window. It'll be at least 12 hours, 8 a.m. to 8 p.m. If somebody wants more than that, you can let me know. I posted this morning a equation sheet, and you can look at that. We have basically one more class worth of material to cover. We will meet on Wednesday. I may have just some, maybe one small topic or something to cover, but it will mostly be Wednesday, a review session, question and answer. You can ask me anything you want. We can go over stuff, anything you want. So look forward to that on Wednesday. And I think that's it. Any questions on logistics or end of semester stuff? Okay, sounds good. I do have one bit of mess that I created on Friday to clean up today. Apologize for that. I wrote down a wrong equation. I knew that at least one of them was wrong last week when we wrote them down, but one of them in fact was wrong. And I have posted it on the video from last Friday and maybe an announcement too. I can't remember now. Anyway, here is the actual, whatever you have in your notes now for these equations, make sure that they are right. Here is relativistic Doppler. And the relevant equations are F obs equals F naught times the square root of 1 minus beta over 1 plus beta. This one was right before. This one was not right before. So Dan, you were right. These should be different equations because they're inverse of one another. This should be 1 plus beta over 1 minus beta. These are all betas. I don't know if you can tell. My pen's kind of running out of ink, and it's really big. So this is the one that was wrong last time. These signs were switched. I had minus over plus. It should be plus over minus. And this is the more important one because there's at least one homework question, like number 1, that requires you to use this one. So apologies for that. Okay. We need to think about momentum and energy today in a relativistic sense. So let's start with momentum. I should have kept the relativistic. Relativistic momentum. Okay, so nobody agrees on the momentum of an object, right? Nobody, since everybody measures a different velocity for different, every observer measure in a different reference frame measures different velocity for objects, nobody's going to agree on momentum. The question is momentum conserved? Can momentum conservation still work with relativistic velocities? And the answer is yes. So can momentum conservation work? And the answer is yes, if we redefine what momentum is. So let me just remind you, obviously, momentum of an object is equal to its mass times its velocity. Where here, again, I'm using u to be the vector of a velocity, of an object's velocity through your reference frame, right? This is v, we were reserved to be a velocity between reference frames. U is the velocity of a particle through a reference frame. So this is exactly the way you defined it in Animal 1, mass times velocity. The relativistic is P equals gamma times M times U. So now, although nobody agrees on what this momentum is. If you're in a different reference frame, we're going to disagree on what this momentum is. But if we all define the momentum of all particles in our reference frame with this value, with this formula, then we agree that momentum is conserved. This is a way to preserve the conservation of momentum. So this is the new and improved and better momentum formula. Also is Newton's second law. Remember, this is F equals ma, but it's really defined F equals dp dt. And if you take this definition from Analyte 1, this is valid with the new definition of momentum, right? So Newton's second law works if we take the new relativistic definition of momentum and take this particular formulation of Newton's second law. Okay. I think there may be some questions on this on the homework. I'm not sure there's anything we have to do with this, but it's useful to see that these things that you learned in freshman physics are still valid if you redefine them slightly in a relativistic way. Okay, that's momentum. That's all I'm going to say. We're going to come back to momentum, but only in the context of energy. So let's talk about energy. In the old way of doing things, there were two kinds of energy. Kinetic energy, which is the energy of motion, and potential energy, which was the energy of position, or shape, or other things that are related to position. Now add a third. Now we're going to add another one. And that is mass energy. And this is the energy of mass. Makes sense. This is probably something you've heard of before, even if you haven't encountered it much in physics classes yet. The mass energy of an object is equal to its mass in kilograms times c squared. E equals mc squared. This, by the way, I told you that Einstein wrote 4 fundamental papers that transformed various fields of physics in 1904. We've already talked about the photoelectric effect and special relativity. This is a third. E equals mc squared. Energy and mass are equivalent, and the coefficient, the constant of transformation coefficient is just c squared. So this is going to change how we think about energy in rather dramatic ways. So let's just think about mass energy and kinetic energy and ignore potential energy for now. Because it's not as important for most relativistic traveling particles anyway. So if we ignore potential energy, then we get something like the total energy of a particle is equal to its mass energy plus its kinetic energy. And that is mc squared plus k. And it turns out that that is gamma times mc squared. And this is weird. The total energy of a particle, that says totat, it should be total. Total energy of a particle, it's mass energy, oh, there should be an mc squared here. Look at me, I'm messing everything up. Mc squared plus kinetic energy, that, as it turns out, is equal to gamma mc squared. Interestingly, the kinetic energy is no longer just 1/2 mv squared. We need a new definition of what kinetic energy is, in fact, that probably is going to have some gammas in it. So we can actually solve this. Mc squared plus kinetic energy has to be equal to gamma times mc squared. We can use this to solve for what the new definition, the relativistic definition of what kinetic energy has to be. So if we solve for K, we get K equals gamma mc squared minus mc squared, or mc squared times gamma minus 1. Remember, gamma is always a number greater than or equal to 1. So that's interesting. This is our new relativistic definition for what kinetic energy is. And it has the mass of the part as it should, right? We mv squared before. Now we still have kind of an mv squared, but there's a gamma minus 1 to give you actually how fast it's moving. So we need to make sure that this has the right limit. In other words, in the limit that beta is very small, does this go to our old familiar, in limit of small beta, this has to be 1/2 mv squared, right? It's not clear that that's going to be the case here, right? If you just, you know that as beta goes to 1, gamma goes, as beta goes to 0, gamma goes to 1, but that's not going to help you. That's just going to make this term go to 0. We need to think about more, we need to think about how the limit as gamma goes to, as beta goes to 0. So let's make sure that this has the right limit. Does it have the right limit? So remember the binomial expansion. If beta is much less than 1, then we can use the binomial expansion to say that gamma is about equal to 1 plus 1/2 beta squared. That was our binomial expansion from before. And so plugging that in, we get that kinetic energy equals mc squared times gamma minus 1, which is about equal to mc squared times gamma, which is 1 plus 1/2 beta squared minus 1. The ones go away. This is about equal to mc squared times 1/2 beta. Beta is beta squared. Beta squared is just v squared over c squared. mc squared times 1/2. Let's say v squared over c squared. I should say just u squared over c squared, because this is not a velocity between reference frames. And this is about equal to the c squareds go away. We get 1/2 times m times the velocity squared, which is exactly what we want in the limit of beta much less than 1. So that's interesting. We have a new definition now of kinetic energy that involves the speed of light squared and this gamma term, and the limit of beta much less than c. It reverts back to our normal definition and expected definition of what kinetic energy has to be. Okay, cool. A useful number for the homework. This is going to be helpful as you're solving some of the homework this week. And that is this number: 1 atomic mass unit. The mass unit that's defined by the mass of the carbon-12 nucleus divided by 12. So hydrogen has roughly 1, helium has roughly 4, the number roughly equal to the number of nucleons in the nucleus, is equal to 931.5 MeV squared, MeV over c squared. In other words, you're going to have to be calculating mc squareds of a lot of things. one atomic mass unit, or roughly the mass of a hydrogen atom, is 931.5 MeV over c squared. So the hydrogen atom times c squared, the rest mass energy of a hydrogen atom, is roughly 931.5 MeV over MeV, mega electron volts. So that's going to be a helpful number to have in the back of your, or just in your toolbox as you're working through homework this week. You don't always have to multiply through by c squared. Sometimes it's helpful if you have an mc squared to divide everything by c squared and just work in this MeV over c squared, basically a mass unit space. Okay. Okay, here is a fourth kind of energy. Actually, I'm not going to say it's a fourth kind of energy because it's really a potential energy. Another kind of energy is binding energy. This one's kind of confusing. So let's try to break it down. It turns out that there is some energy associated with objects being held together in some way. So in other words, there's binding energy associated with the electrons in an atom. It takes some energy to remove that electron from the atom. There's binding energy associated with the nucleons in an atom, meaning the protons and neutrons. It takes some energy to remove, say, a proton from the nucleus of an atom. And in fact, that's what binding energy is. In fact, that's what potential energy is. If a gravitation, the moon and the Earth have some potential energy associated with them, what is that potential energy? It is the energy that it would take to separate the moon and the Earth and take them to infinity. Binding energy, exactly the same thing for particles in molecules and atoms and nuclei. It is the energy that it would take to take that, or take some component or all of the components of a compound system and remove them to infinity. Okay, and this has some energy associated with it. So energy associated with particles being held in place. It's really a potential energy. Okay, so for example, let's say we have a water molecule, H2O. What does that look like? Well, you've got some oxygen atom, and you've got some chemical bonds, and two hydrogen atoms sticking attached to it at some level like this. So we can talk about the entire energy of this H2O molecule, and let's say E naught. This is basically the rest mass energy. This is assuming that this this water molecule is at rest. What is its energy? It has some energy just by being there and existing because it has mass. This is going to be equal to the mass of the H2O particle times c squared, right? The rest mass energy is just the mass of that particle times c squared. That is sort of the definition of E naught, the rest mass energy. This is equal to the mass of an oxygen atom times c squared. I was just going to put O for oxygen, but then it looks like an M naught, and I really want that to be capital O. So I put an X there to make you realize that this is the mass of the oxygen atom by itself times c squared, plus 2 times the mass of hydrogen, because there's 2 of them, times c squared, minus the binding energy, where the binding energy is greater than 0. So this is the energy, again, that it takes to take all of these, the 2 hydrogen atoms and the oxygen atom, and separate them all to infinity, right? So what is the mass of H2O? We can solve this equation for the mass of the water molecule now. Just divide through by c squared. The mass of the hydrogen atom is mass of the oxygen plus 2 times the mass of the hydrogen minus this E binding energy over c squared. The mass, again, and this is a positive number, so we're subtracting a positive number. The mass of an H2O, of a water molecule, is a little bit less than the mass of the oxygen and the 2 hydrogen atoms that make it up. Mass is not conserved. Nuclei work in the same way. The mass of a helium-4 nuclei is less than the mass of 4, or less than 4 times the mass of a hydrogen atom, because some of that energy is gone into holding those nuclei together in the nucleus. And this, in fact, is the fact that makes it possible for the sun to generate energy. You take 4 hydrogen atoms, you fuse them together to make a helium atom, and eventually, and you've released a little bit of energy. And that energy is what powers the sun. So mass is not conserved. Energy is. And if you consider, well, mass by itself, energy is, and mass is if you can consider mass just being a form of energy. And then energy conservation is all you really need to worry about, because mass is just a form of energy. Okay, so there's some problems in the homework assignment that will ask you to figure out what these binding energies are, and or maybe some differences in masses, and this is the way you're going to go about doing it. Okay. Some more, this gets kind of interesting and weird and bizarre fast. So let's think about some implications of the things we've just written down. So this is under the category of interesting things about momentum and energy in the relativistic sense. I might have to switch to red here because my black marker is running out of ink fast. Let's see how red's doing. Oh, much better. Interesting things about momentum and energy. Here we go. We know that P, that momentum, is equal to, the new way we define it is gamma times m times u. That is going to be, with our definition of gamma, we can pull it in, divided by the square root of 1 minus beta u over c, beta squared, which is u over c, quantity squared. If we square both sides and multiply by c, we get p squared c squared equals gamma squared c squared m squared u squared. Again, I'm taking this part, squaring it, and then multiplying by c squared on both sides. We'll bring this in later, but for now, square it and multiply by c squared, and you get straight from there to there. Momentum squared c squared, gamma squared c squared, m squared u squared. Okay, so this, we can call this, say, pc squared is gamma times m times c squared squared. So let's see what I did here. Gamma times m times c, that's all there. We've got a c squared here, though, which is now to the 4th. So we need a 1 over c squared, and we get a u squared over c squared on the outside, right? So all I've done is taken this, bring it into a square, and divide by c squared and put another c squared in here. But what is gamma mc squared? We define.
There's also a question in the chat.
Is there?
Yes.
Let me see. That's fun. Is U or just V, or is it different? So U and V are different. I'll try to be clear when I'm using which. U is the velocity of an object through your frame. V is the difference in velocity between two frames. So they are kind of the same if you're talking about moving from one frame to the other, but U is a more general thing. It can be anything. We're not even be thinking about changing reference frames to that. So U is just a velocity of a particle through our reference frame without thinking about another reference frame change. Make sense? But back to my question, what is this gamma MC squared? We defined that on the previous page.
The mass energy.
It is MC squared is mass energy. What is gamma MC squared?
Kinetic energy, right?
That was not quite the kinetic energy. Kinetic energy was MC squared times gamma minus 1.
Total energy?
Total energy.
It was the total energy. We defined gamma MC squared to be the total energy of our particle, right? This is, where am I? This is E tot squared. And what is U squared over V squared? That's just beta squared. So this is fun. We've got now an equation for beta. Let's solve this for beta squared. Beta squared equals momentum times c squared divided by the total energy squared. We can square root everything and we get beta equals momentum times c over the total energy. This is useful. I don't know, this is a useful equation for beta. Again, this isn't going to be obvious, right? If you want to know the velocity of something and you've got its total energy and its momentum, it might not be obvious that just dividing those two numbers gives you beta, but it does. And this is going to be useful for the homework, particularly number 13. Okay, we can eliminate beta altogether because we know that gamma squared is 1 over 1 minus beta squared. So 1 minus beta squared is 1 over gamma squared. And that means that beta squared is 1 minus 1 over gamma squared. So we can plug this into this and get this. P squared times c squared equals gamma MC squared squared times 1 minus 1 over gamma squared. And this is gamma squared times MC squared times m squared times c to the 4th.
Can you bring the screen down a little bit?
Yes. Is that better?
Yeah, it's fine. Thank you.
Okay. It just says PC squared on the left. Yep. And all I'm doing now, so I took this equation and I plugged in this beta squared, and I actually took this equation, plugged in this beta squared, and now I'm just multiplying it out, right? So I've got the 1 gamma squared MC squared m squared c to the 4th, and now I've got a minus term, and I've got a 1 over gamma squared here term. And the gammas actually cancel out on this term, right? I got a gamma squared and a 1 over gamma squared. This is just m squared c to the 4th, right? And this, as we know, is the total energy squared. And this is the rest mass energy squared. So I'm running out of room, but let me move back up to the top. This implies, if we solve this for E tot squared is equal to p squared c squared plus m squared c to the fourth. So we've got our total energy. Oh, no, I'm too high now, sorry.
Thank you.
We've got our total energy. We've got the momentum, so the total energy squared, the momentum times c squared, and the rest mass energy squared. Right? I don't know why, but it's very tempting to just want to cancel out all of these squareds, but of course you can't do that. If you take the square root of this side, you have to take the square root of this side, and you have both of these terms still squared under the square root, which you can do, but don't, it's wrong to just take the square root of all and eliminate all of these and just make it E tot equals PC plus MC squared. That's wrong. So this is a cool equation because it's got momentum and total energy all in one place, which is kind of fun. How about photons? This is kind of cool. Photons, as you know, have no mass, but you can still write this equation down for photons, right? E squared still equals PC squared plus MC squared squared. In this case, though, for photons, M equals 0, and this term goes away. So now we can take the square root of both sides, and now it just becomes E equals P times C. Hence, even though photons have no mass, they still have some energy, and therefore you can calculate their momentum. And in fact, if you solve for that momentum, you get exactly the equation that we wrote down for the momentum of a photon earlier, even though we had to completely wave our hands to figure out why that was the case. It now just falls right out of our definition of energy. And photons do have momentum simply because they have energy. Okay, so we have some last bit of tidying up to do. And one bit of tidying up I want to think about really quickly is photons and gravity. Not really tidying up, but a preview of some things that you might run into later on in your physics career. So remember, actually, let me erase this and start at the top because I'm gonna need some room. So remember, special relativity, which is what we've been talking about so far, is the special case of inertial frames, meaning non-accelerating frames. You have one frame moving at a constant velocity with respect to another one. So only non-accelerating frames. General relativity, which took Einstein another 10 years or so to work through completely, extends that theory to accelerating frames. We need the tools of general relativity to really be able to say some substantive things on this. And there is a gravity class that's offered in the junior and senior year, which will start to develop those tools and give you some insight on how they work. But we already have enough insight to at least see how there's some problems that need addressing. So we already know that mass and energy are equivalent. equivalent. We can, in fact, we can define the effective mass of a photon. We know, of course, that photons have zero mass, but we can talk about the effective mass of a photon based on its energy. We know that the energy of a photon is equal to h times f, Planck's constant times its frequency. And if we just set that equal to mc squared, that defines a rest mass of a particle that has the equivalent energy of that photon. That sort of gives you the effective mass of that photon. Solve this for mass, you get m equals hf over c squared. So, according to, remember, I mean, this is sort of one of the ways in which Newtonian mechanics fails dramatically, right? According to classical Newtonian mechanics, what is the force, the gravitational force between two objects? The gravitational force between two objects, according to Newton, is, you can write down the equation. This is the non-relativistic. According to Newton, force of gravity is the gravitational constant times the mass of one object times the mass of another object divided by their distance squared. We'll call it r, right? So in the case of a photon, which has zero mass, Newton would say photons are unaffected by gravity. A photon could travel past a very massive dense object and would not experience any force due to gravity because its mass is zero. No matter what the mass of the other object is, if one of these is zero, it goes away. But Einstein says, not so fast. According to GR, mass and energy bend space-time. Photons are no exception. And so space-time itself has some curvature, and gravity is nothing more than objects trying to move in a straight line through that curved space, right? The moon is moving in the straightest path it can, given the curved surroundings of its environment, specifically an orbit around the Earth. And same with the Earth around the sun, and the sun around the center of the galaxy. All are moving in the straightest line they can. It just happens to be that the path is, that the space that it's moving through is curved, and that, from an outside observer, looks like a curved path. And photons are no exception to this, right? Even though they have no mass, they certainly are traveling through a curved space-time, and they will be affected by that curved space-time. Photons have to be affected by this. This was one of the major predictions of Einstein's general relativity theory when he published it in the mid 19-teens. And it was one of the first tests that was made because he realized that this could be tested. Because the sun, as starlight passes the sun, that starlight, let's actually draw a diagram. Here is the sun. As starlight passed relatively close to the sun, it should be deflected slightly as it passes very near the sun. And so Einstein did the calculations. How much should it be deflected? And it turns out it was a very small amount, even for starlight passing just beyond the limb of the sun, right? And so this is a very difficult observation to make, obviously, because the sun is really bright, stars are really faint, and you can't usually see them right when they're next to the sun. However, in very special circumstances, you can. And those circumstances are, even in the 19-teens and early 1920s, when these experiments were being carried out, that it happens during a total solar eclipse. So the moon passes in front of the sun, and for a brief period of a minute or two, you get a completely blocked sun. The stars come out, and you can actually observe stars that are right near the limb of the sun. And so Einstein predicted how much this bending angle should be. Stars that should be in a particular spot should be deflected a little bit to be in a different spot because of this bending of light. And I think the first solar eclipse expedition that was made was either cloudy or the equipment didn't work or anything, so they had to wait 6 months for the next total solar eclipse to come, or a year. Again, you're traveling to wherever that solar eclipse happens to be, which is a very small path on the Earth for any particular eclipse. But they went and they observed it, and sure enough, the number that they got, they found that those stars had moved a little bit, and by almost exactly the amount that Einstein had predicted that they would be. So that was the first major victory for Einstein's theory of general relativity. Of course, today we have observed many more instances of this. The most dramatic of them are, let me share my, so to see the biggest effects, you need to look at the biggest objects in the universe. And the most massive objects in the universe, at least on a measurable scale, are galaxies of clusters of galaxies, right? So here is a small cluster of galaxies that maybe has a few dozen galaxies. In practice, we see the most striking effect with galaxy clusters, superclusters that contain thousands of galaxies. But the general idea is the same, right? So the mass, why did light curve around the sun? Because the mass of the sun was warping the curvature of space-time around it and causing photons that were trying to travel in a straight line to appear to move in a curved path. Well, the same is true of galaxy clusters. In fact, there's obviously way more mass in a galaxy cluster than there is in the sun. Of course, it's spread out over a much larger area, but it creates some potential well of curved space-time that photons will experience as they travel through this region of space. And it will deflect photons that happen to be moving through that region. And so if you have for instance, a foreground galaxy cluster, and you have a background galaxy, the light from that galaxy can be bent around, and you can actually get multiple images of this particular galaxy that reach the Earth that travel in different directions. So in fact, the galaxy is here, but it looks like it's here and here, and it's going to be spread out and smeared over some interesting way. And we actually see this happen. Here is an example of such a thing. This is, again, the foreground. In the foreground, you have this very rich galaxy cluster. All of these sort of yellowish, smeary things are galaxies within that galaxy cluster itself. You also, though, see a bunch of these streaks in the background. These streaks are not galaxies within that cluster. They are background galaxies. And they are streaked because the light from those galaxies has been bent and warped and not in some nice regular way as that galaxy light passes through the foreground. These are background galaxies that have been lensed by this foreground cluster of galaxies. And I don't know for sure, but clearly there's a lot of them. It has to be pretty close to our line of sight. So all of these streaks that you see here are from galaxies that are pretty much lined up with our line of sight, but we're seeing the light bent through in different directions. And it's possible that, for instance, this image down here is exactly the same galaxy as this image up here. It's just been bent in opposite directions and reaching us from opposite directions. But we can use this to, for instance, measure how much mass is in this galaxy cluster. And lo and behold, what do we find? We find that there's way more mass in this galaxy cluster than can be explained by adding up the masses of the stars and the individual galaxies that we can see. And this is one of our major pieces of evidence that there's dark matter out there. In fact, we can't account for 95% of the mass that's in this galaxy cluster, given the angles of the bend of these lensed images around it. And that's just one of many pieces of evidence that there's dark matter out there. So it all sort of adds up, and it's cool. So coming back to special relativity though, photons and general relativity, photons are affected by the curve, mass and energy curve spacetime, and that can affect photons. And here's a dramatic example of photons actually being affected by the mass of particles, of objects as they travel through space. Okay, I've got one more thing today, and that is to think about, we actually already have some insight as to why space has to be curved. So let's think about that real quickly in the 5 minutes that I've got left today. Let me stop this share and move back to this share. So you might remember in the last problem set, there was a question about circular orbits, right? There was one question that asked, hey, what if an object moves out in a particular line, a straight line, turns around and comes back? What is the time difference between those, between the clock on the ship and the clock that stayed on Earth? And then the next question was, well, what if the observer had gone on a circular path instead? Would there be a difference? Well, let's consider that. And instead of making, let's say, this path where you start at some point and then return to some point, let's say you're taking this circular orbit from the perspective of somebody who's in the middle of that circle. What would somebody traveling in a relativistic speed in a perfect circle around another observer? The question asked us to think about the change in times. Well, let's not think about the change in time. Let's think about the change in positions, right? So let's say the orbiter is moving at constant speed. Obviously, the orbiter is not moving at constant velocity because its direction is changing as it goes around. So this is a non-inertial frame. We cannot just apply special relativity to it and expect our equations to work. They will not. This is a non-inertial frame. It is undergoing, in fact, constant acceleration. But interestingly, that acceleration and that velocity is always perpendicular. The acceleration is always parallel to the line of sight, and the velocity is always perpendicular to line of sight. So we can think about some of the consequences of this motion. One of the consequences, we know that this observer will see a shorter path length for this particular loop than an observer at the center who is stationary. This is length contraction. Let's say delta x is the total path around one loop. Interestingly, what do they have to say about the radius? Since the velocity of the orbiter is perpendicular always to the velocity to the rest frame, to the Earth, they actually always have to agree on what r is, because that is never along the line of sight. It is always perpendicular, not the line of sight. It's always perpendicular to the velocity, right? And length contraction only happens in the direction of motion. So they have to agree on R. How is it possible for them to agree on the radius of a circle, but disagree on its circumference?
One of them
It's
sees an
only-
ellipse.
Sorry?
Does one of them see an ellipse?
They both will see a perfect circle. The only way this is possible is if space-time itself is not flat. The only way this is possible, see if I have some globe. I know I'm out of time. Let me just pull this down and see if I can convince you, right? If you have, let's say, a person standing on the top, on the North Pole of the Earth, let's call him Santa Claus, and you've got some reindeer, I don't know, let's call him Comet or something, moving around in a circular orbit. Here is a case, right? They will both agree on the radius of that orbit, but they will not measure 2 pi r for the radius for the circumference of this orbit, right? Because this space is curved. In fact, it will be less than 2 pi r if you measure it just a circumference around the North Pole at some non-90 latitude. So that is our hand-wavy, very special relativistic way of sort of seeing how it must be the case that space-time is curved in the case of an accelerating reference frame. It's the only way to explain how this is possible, where the circumference of a circle is less than 2 pi r. All right, that is all I want to talk about today. You're welcome to ask me about this stuff and any other things you would like on Wednesday. Good luck. I'll have normal office hours on Wednesday and also on Thursday. So enjoy the rest of your Monday.
Thank you too.
Have a nice day, Professor Steiner.
Thanks.
Have a
You too,
nice
Tom.
day.